All right, good morning, everyone. Thank you for coming to the confidential computing session. So the session is all about security and privacy for the cloud. So it's great to have you here. And we have sort of a very exciting group of speakers. And the list of achievements and awards that they have is so big that I had to print a page of paper just to remind myself. So I think it's going to be an exciting session. The first speaker is Mark Rusinovic. Mark is the Chief Technology Officer for Azure. He's an expert on distributed systems, operating systems, and he has the pleasure and the responsibility of running one of the largest distributed systems ever built by mankind. So it's a tough job. Mark is also an author of several books. He has run startups. So he has a sort of very broad range of experience, and he's going to tell us about Azure Confidential Computing.
Yep, and we found out yesterday Donald hasn't read my book. But
I was going to say, I'm putting it on my reading list.
Okay. Good. Good morning, everybody. So this morning I'm going to talk to you a little bit about what we call confidential computing and our vision at Microsoft in Azure, specifically with MSR, on how this technology is going to evolve and eventually, I think, become standard for all computation. I'll start by talking about the way that we approached it in Azure, starting 8 years ago when I began in Azure. Even back then, people were looking at the cloud skeptically for a lot of different reasons, but one of them, of course, a big one, was the security of their data in the cloud. The various threats that they thought their data would be exposed to if they stored their data in a cloud provider where it's being managed by somebody else, including, for example, a hacker breaking in through the multi-tenancy boundary and getting access to their data, malicious insider taking their data and releasing it, or a third party coming and then, through legal means, coercing or having the cloud provider turn over the customer's data, and all of these without the customer's knowledge. And all of these, we wanted to make sure at Microsoft that as much as possible we could protect the customer's data in light of these threats, and specifically for the legal request for customer data, that we wouldn't be put in the middle, that it would be a matter between law enforcement and the customer. And so we started looking at how we could increase the protection of our data. And if you take a look at the way that cloud providers have evolved the protection of data, of course, one of the things we've seen over time is that all of us have put in mechanisms to encrypt data at rest, starting with system managed keys and then adding customer managed keys, or bring your own key solutions for customers to protect their data. We've always encrypted our data in transit between data centers, and you're seeing us introduce encryption even if the customer's data links aren't encrypted within the data center. And then the missing piece, though, was how do we protect the data while it's being computed over? These mechanisms where customer would store their data encrypted in the cloud, but then not be able to compute over it, are fairly uninteresting to the customers and to us. At that point, the cloud is just a giant storage solution. The customer's still left with providing computational resources outside the cloud and having to worry about transmitting data back and forth. If we could bring the computation to the data center and still protect the data, then we'd achieve protection of the data through all aspects of its life cycle. So we saw the development of what are called trusted execution environments. I believe everybody in the room here is probably familiar with them, so I won't spend too much time on them, other than to say that the interesting characteristics with respect to the problems that we're solving here are the fact that it's a black box. From outside the black box, you can't see what's going on inside the black box, ideally. And the black box can attest to what code is inside the black box in a secure way. And then the black box can also seal secrets inside of itself for later access. The two examples of enclaves that we've seen that are in practical use for cloud providers would be SGX, which is part of Intel processors, and then virtual secure mode, which is a technology that was released in Windows Server 2016. Unlike SGX, which is hardware protection of the data, virtual secure mode is hypervisor protection of the data. So even a host partition, a privilege partition, a system administrator wouldn't have access to the data being protected by the virtual secure mode black box. The trusted execution and application architecture that we see resulting from these technologies, where the enclave, we could process isolation, sub-process isolation, the black box actually lives within a process in the operating system, shares the address space of that process. So what's inside the black box's portion of the address space is trusted, and from the outside, that's untrusted, but the trusted portion can reach outside of the black box and access data for efficiency's sake. Rather than having to copy data back and forth inside, it can access encrypted data that is outside the black box. And this requires a decomposition of the application into these two pieces, the trusted portion and the untrusted portion. So Azure Confidential Computing, looking at these technologies, we realize that there's a lot more than just making black boxes or SGX available to customers or virtual secure mode available to customers. There's a lot of other pieces that we needed to fill in. And so if you take a look at all of what we consider confidential computing in Azure, it consists of everything from making these enclaves available, and we now have SGX clusters stood up in Azure that we make available through a limited preview form for customers that sign up and want access to them. We also are working on an SDK that enables developers to develop these applications that are decomposed into the untrusted and trusted portions with a fairly easy way for them to access functions from outside the black box, inside the black box, and have the underlying SDK runtime take care of the transport and the transitions between the enclave and the outside world. We're also working on an attestation service. This is, of course, necessary for trusted code on the outside to verify the integrity of the trusted or code on in the inside of the enclave. That attestation that comes from the enclave provider, whether it's the hypervisor or the hardware, needs to be validated someplace. And that validation is coming in the form of an attestation service. So we're in the process of building an attestation service, one that will attest to SGX enclaves as well as other enclaves technologies as they come out, so that the software either inside the data center or outside the data center can verify the authenticity, integrity of this code that's inside one of these enclaves, and that it's actually a trusted enclave. Finally, one other aspect of it is, actually two other aspects that we need to mention, are that we're looking at also providing confidential computing capabilities inside of our PaaS and SaaS applications as well. So making it very easy for customers to consume these rather than having to build applications. Of course, all these are necessary from the building blocks to create these applications up into finished services that end users can take advantage of when they're accessing their data or processing their data. And then finally, one of the key aspects of the collaboration with Microsoft Research has been looking at how we can harden these black boxes. Most of you know here that black boxes, these enclaves, SGX specifically, have been subject to side channel attacks. And so we're looking at ways to prevent leakage of data outside of an enclave, either through side channel or through corruption of the enclave's code or exploitation of bugs in the enclave code. And that's an ongoing research problem with Microsoft, with MSR. So speaking of the information leaks, the side channel attacks, being able to look at the execution of the enclave from the outside, seeing its behavior through page faults, memory accesses. This is one of the examples of a side channel leakage that could potentially reveal information about the data that's being processed inside the black box. One of the papers that struck me as fascinating was one by Microsoft Research, where by looking at page faults, they were able to reverse engineer the JPEG images being processed by a JPEG decoder to close enough where you could get a pretty good idea of what the image looked like. And so these kinds of problems we want to protect against by having a verified runtime, an instrumented application that does two things. One, prevent the enclave from releasing secrets to the outside, and the other one is to prevent these information leaks by looking at the side channels of the execution from the outside. And so this is just a simple example here of, actually that should be animating, for some reason it's not, but the idea is the data comes in, and depending on the tree, different parts of the address space or different cache lines or pages are accessed, and you can reverse engineer which paths through the decision tree the code took. So I want to show you an example of one of the projects that MSR Cambridge has ongoing, which is oblivious computation, the protection against these inadvertent side channel leaks. And I'm going to show you by taking a look at support vector machine execution. And did you change the password on this? I did that. What? No, I did that. Sorry about this. This is a secure login here. Too secure.
Oh, because I know why.
Oh, here it goes.
Because it's
All right.
not on the power.
Okay, so this is the example. First trace I'm going to show you is a tool that monitors the execution of memory accesses and code accesses of the support vector machine computation as it's processing data. And you can see for much of the time that these traces actually do not line up based off the two different inputs, A and B. And that is an example of how we could look at the differences or look at the trace execution history and reverse engineer the data being processed by the SVM algorithm. On the other hand, a version of the SVM algorithm that's been fed through the oblivious computation compiler executes, and no matter where we stop the trace, you can see that the trace pattern is exactly the same for both data inputs A and B. And so we view this as one of the ways that we can help developers protect against leakage of side channel attacks. And there's still a tremendous amount of research going in this space. There's some performance overhead, as you would expect, to this kind of oblivious modification of the code. And that overhead varies depending on the algorithm. Research work is ongoing to minimize that overhead. Let's talk about some of the examples of confidential computing that we're also exploring, both in the Azure product group as well as with MSR. And start with one of them, which is always encrypted storage with SQL Server. And let me talk a little bit about that one. I'll talk about confidential blockchains. There's financial data processing, and there's secure multi-party machine learning. When it comes to SQL Server, the way that customers today protect their data from access by the cloud provider or by the hoster is to use a feature called SQL Always Encrypted, where they have the key on the client side, the SQL runtime, client runtime, transparently takes that key and encrypts data on the way into the SQL Server and decrypts it on the way out. So the data is always in encrypted form on the back end in the server. The downsides of this, though, are that the SQL Server is not able to see the data and therefore not able to perform rich expressions on top of the data. Some simple comparisons, if you're using a symmetric encryption algorithm like equality, are possible, but certainly not ranges. And so with confidential SQL version of Always Encrypted, which is something we've announced is coming, and we're working with the SQL product team to get into released form, the SQL data is processed inside the database engine is executing inside of an enclave, and the data is encrypted on the way into the cloud, and then the keys are released after attestation of the SQL engine to the SQL engine so that it can process the data. And in this case, you get arbitrary rich expressions just like you would with unencrypted version of SQL. The data remains encrypted in flight, it remains encrypted on disk, and it remains encrypted as it's being computed over. Another scenario, like I've mentioned, is confidential blockchain. And if you take a look at the way blockchains have evolved, they started with absolutely no confidentiality at all. So the Bitcoin and Ethereum networks, everybody that's participating in that network can see everything that's going on. In fact, that's a property that's necessary for the security of those networks. And over time, we've seen different paths being explored for providing confidentiality, like side chains and like zero-knowledge proofs. All of these add a significant amount of complexity to the interactions with the blockchain and the construction of the blockchain, and they have limitations as well in terms of their scalability and how much data then can be shared by the network itself versus sent off into a side chain that only the parties involved with that can see, and therefore makes it very difficult to take that data off those side chains and make it available to other parties that weren't part of that. Further, zero-knowledge proofs, for example, have a high computational overhead, and so that will slow down the execution of the blockchain. By placing the blockchain network within a network of trusted execution environments where they attest to each other the code that they're running, the parties that are governing the individual nodes can certify which code they trust, including the blockchain code, as well as the Coco runtime code, the Coco being the project name for this, which stands for Confidential Consortium. That code establishes this network and then implements the basic runtime primitives that a blockchain ledger can be layered on top of. And this includes secure storage of the blockchain network on disk, as well as the secure release of this information to parties that should have access to it, which makes possible a few things. One of them, extremely high transaction throughput and extremely low latency. Because once you end up trusting the nodes in this way, the nodes trust each other, you can fall back to crash-tolerant consensus algorithms as opposed to PBFT algorithms or proof-of-work algorithms. Further, because everything that happens in the enclave is trusted, you can program arbitrary confidentiality rules into that code through governance policy. One of the very common scenarios we've heard is that multiple parties are transacting with one another inside the blockchain. They should only be able to see their own transactions, but there's an auditor that is part of this consortium that needs to be able to see the transactions of multiple parties. And so how do you set that up in a dynamic way? It's actually very straightforward if you've got a network like this, because you just implement those confidentiality rules as you would in any trusted network, which is simply through access control policies, where the auditor has access to arbitrary transactions in the code inside the enclave that's part of Coco with the blockchain primitives laid on top of it would only make those transactions available to authorized parties. So confidentiality, the governance can also be built in to vote on which parties can be added to the blockchain as well as to evict parties, all with very high throughput and low latency, like I mentioned. This is a picture of the Coco architecture. Now, Coco, what we've done with Coco is created a prototype last year that we actually demonstrated publicly when we announced Coco to the world. The Coco prototype has evolved now, and we're building a production version of Coco. This runtime, like I mentioned, arbitrary blockchains can be layered on top of. And so this initial prototype, we're layering the Ethereum blockchain on top of it. So it's compatible with off-the-shelf Ethereum, though with confidentiality attributes added to Ethereum. So you can specify confidentiality on top of smart contracts. This project we intend to make completely open source. And that means that customers can take this and run it on their own servers outside of Azure. The goal here isn't necessarily to make sure that this is locked into Azure or Microsoft-only technologies. It's open source. The Enclave runtime that we're working on will support both Linux and Windows. Coco will eventually support both Linux and Windows, and it will be published in GitHub for other parties to participate in the development of it. We also expect other blockchain ledgers to be integrated on top of Coco over time as well. So let me show you a quick example of Coco. And what I'm going to do lost track of this one. Oh, here we go.
Is it locked up again?
Nope, I don't think so. Yep, it's locked up. I don't know why it's doing this. This is SSH session to a Linux machine that is running in Azure, an SGX machine. what's going on.
I don't know why.
So what I'm going to do first is show a simple smart contract. Oh. Thanks. So I'm going to show a simple smart contract executed on the Ethereum Coco integrated blockchain. This is standing up a 5-node Ethereum network, and then will execute as many transactions as it can, and then show us the throughput that it achieves. And of course, on the public version of Ethereum, which is based off of proof of work consensus, the transaction throughput's 10 to 15 transactions per second. You can see here, then again, this is Ethereum, stock Ethereum integrated with Coco, and it's achieving, you can see, around 12,000 transactions, 13,000 transactions a second. We've also, just to push the limits of the Coco framework, just created a simple ledger network and then integrated that with Coco. And this is standing up a 5-node version of that network, and then also trying to see how fast we can drive it. And you'll see that it's significantly higher than what we got with Ethereum, and yet there's still more performance optimization to do. So you can see that we're achieving close to 100,000 transactions a second. We think we can get up to 150,000 transactions a second or higher in the 5-node network here. And then finally, one of the last cases that we're looking at, and this one's very exciting from a number of different domains, is multi-party confidential machine learning. One of the canonical scenarios for this is the processing of medical data, where different parties are coming together with health information gathered from different sources, whether x-rays, it's CAT scans, other diagnostic data. These parties are bringing it together, and they can get a deeper insight than any one of them individually can, but there's regulatory restrictions or privacy concerns over sharing their data with these other parties. With confidential computing and these enclaves, they can, if they trust the algorithms running inside the enclave, release keys that make the enclave or enable the enclave to access their data and then perform this multi-party computation over it. And so I'm going to switch back and show you a very quick demo of that. This is the hospital scenario with 3 parties. So we have the server. This is where the training will happen. We've got hospital A. We've got hospital B. And I'll show you hospital A is taking its plain text data. It's going to encrypt it. And then it's going to encrypt it with the server key that came from the enclave. And now the server will process the data, show the encrypted model outside the enclave, and then when we go back to hospital A, hospital A, you can see hospital B is getting back the encrypted weights and decrypting them with its own key and then showing them. So in this case, hospital A and hospital B were able to get insights out of their data without either one having access to each other's data, just trusting that machine learning algorithm and the trusted execution environment it was executing in. So that's a quick look at confidential computing. We fundamentally believe in Azure that we're at the beginning of a transformation of the way computing is done. Today, because of limitations in enclave technology, we'll see this only for very kind of extreme cases of customer sensitivity over data. We expect that this will unlock data that would otherwise not come to the cloud and allow it to come to the cloud. But that over time, these primitives are powerful enough that we will see the creation of effectively the equivalent of these private data centers, on-prem data centers within the public cloud, protected with enclave technology. Also, as part of our intelligent edge, intelligent cloud strategy, of course, enclave technology will be critical on the edge to protect data, sensitive data, as it's being processed on and collected from those edge devices. So with that, I want to thank you very much for taking a look at our confidential computing program few things I want to emphasize. This is open source, tight collaboration with MSR. We'd like and seek collaboration with the research community on these projects that I've talked about. There's a lot of spaces to explore here, and we don't think we're going to be the ones that can do all of it. So collaboration is certainly welcome. And just want to highlight Manuel Costa. Where is he? Where'd he go? Oh, there he is, right in front of me, from MSR Cambridge, who's been the lead collaborator with us in Azure on this project. So I'll go ahead and turn it over to the next speaker. Thanks.
Let's thank Mark. I think we have time for a couple of questions, and then all the speakers will be around. But let's keep the questions short. Let's take 2 questions. Yep.
Could you please comment on how you will extend these enclave technologies to accelerators, given that Azure is now incorporating accelerators and there are more to come?
This is an area of ongoing research. I don't really have anything more to say about it other than we are exploring how to do that. Of course, the machine learning example highlighted the need for that. The training, which is not best done on CPUs but done on accelerators, is one of the scenarios that we're looking at very closely.
One more question?
Maybe just an answer to Babak. This morning, Stavros Boulos was presenting. So there is at the tech demo during lunch, you can find Stavros, and he can tell you a little bit about his research. Right? There was a small pitch this morning.
Thank you. Yep.
I have a quick question. Could you please comment something on the use of homomorphic computing in Azure and how practical that is nowadays?
Yeah, so that's another big effort in Microsoft research is homomorphic encryption, and we watched the development of that very closely as well. It's got some limitations. It has performance overheads as well associated with it. We don't think necessarily this is a one-size-fits-all space, and in fact, homomorphic encryption inside of an enclave, the combination of the two is something we're also looking at as ways to extend the power of homomorphic encryption.
All right, let's thank Mark again. Thank you very much.
Thanks.
So our next speaker is Don Song. Don is a professor in the electric engineering and computer science at Berkeley. Don has a very broad range of interests in security, ranging from software security, network security, distributed systems, applied crypto, blockchain, and machine learning and security. Don received a very large number of awards, including the MacArthur Fellowship, the Guggenheim Fellowship, the NSF Career Award, Sloan Research Fellowship, MIT Technology Review Award, and many others. I would highlight that Don is ranked as the most cited scholar in computer security, so that's a special achievement. So we are very lucky to have Don here today. Thank you very much, and I'll hand over to you.
Okay. Yeah, thank you. Thank you, everyone, for being here. Today, I'll talk about towards secure, practical, confidential computing with open source secure enclave. And now, wearing 2 hats, I'm a professor at UC Berkeley in computer science department, and also I'm the founder and CEO of a new startup called Oasis Labs. So here, we hear a lot about the value of data analytics and machine learning. They can really bring us a great power in terms of gaining insights from data and help us to make better decisions in many different areas, including healthcare, IoT, smart building, many different, and financial services, many different areas. And also, as we all know, data is the new oil. Unfortunately, a lot of this data also is very sensitive. So as we use the data, we need to be very, very careful with protecting users' privacy. So first, let's look at how current framework works for data analytics and machine learning. So how current framework works is that users' data is being collected, and then the analyst will write an analytics and machine learning program. And this program will then run on the computation infrastructure, which then computes the results. However, the current framework is insufficient for security and privacy protections for a number of reasons, and in particular for several different types of threats. So the first type of threat is that the analytics and machine learning program itself actually may be untrusted because there can be insider attacks, or the analyst's account may have been compromised, and hence the attacker can actually inject malicious programs into the analytics and machine learning program. And also, the second threat is the computation infrastructure itself may be untrusted as well. Again, attackers may have compromised the computation infrastructure and hence can then steal sensitive data during the computation process. And finally, the computation result itself can reveal sensitive information about the inputs as well, because these computation results actually are computed from the sensitive inputs to start with, and hence the computation results itself may reveal sensitive information about the inputs as well. So to address all these three different types of threats, we need to develop different types of technologies. And this is something that my group has been working in. So, so first, to address the threats of computation outputs revealing sensitive information about the inputs, we have been developing technologies in building practical solutions for differential privacy. And for addressing the threats of untrusted data analytics and machine learning program, and we have been developing technologies for program rewriting and verification so that we can actually automatically rewrite the data analytics and machine learning pipelines to ensure that even though the original analytics and machine learning program may be untrusted, the rewritten program will be ensured that it will satisfy the desired security and privacy requirements. And to address the threats of untrusted infrastructure, we leverage technologies for secure computation. Given this session is on confidential computing, this is the area that we will actually focus more in this talk, the secure computation side. I wanted to show this overall picture just to explain that when we do data analytics and machine learning, the privacy and security aspect is actually fairly broad. We need to actually protect the security and privacy of data from many different angles, not just confidential computing. And it's important that we actually combine these different technologies to really ensure the security and privacy protection for users' data. But for this talk, we will mainly focus on addressing the second type of threats listed here using secure computation to protect against untrusted infrastructure. So the concept of secure computation is very simple. The goal is essentially to be able to simulate a trusted third party where essentially users' data is being used to compute a certain function. With this simulated trusted third party, we can ensure that from the computation perspective, users' data is being protected. So an attacker will not be able to see more than, in this case, the computation results. And also, in this case, we also want to ensure that the right program is being executed and it does the right things. And one example illustrating the importance of secure computation is, for example, we want to build a word embedding model from users' text messages. And of course, users' text messages are really sensitive, and the computation infrastructure may not be trusted. So we want to enable the secure computation so that we can build the language model in this case while preserving the privacy of users' text messages. And when we talk about secure computation, there are two main types of approaches. The first one is cryptography-based approach. And the second type is a hardware-based approach. So with the crypto-based secure computation, there are different techniques, including fully homomorphic encryption as well as secure multi-party computation. The challenge for crypto-based secure computation is that the performance overheads can be very high. Oftentimes, it's orders of magnitude performance overheads compared to native computation. And this, because of this, it significantly limits the usage scenario for crypto-based secure computation. The second type of approach for secure computation is hardware-based, in particular leveraging secured hardware to enable an abstraction that we call trusted execution environment, also called a secure enclave. So in this case, a secure enclave can provide the capability of hardware-based isolation as well as attestation. And the advantage of secure hardware is that it can provide really, really good performance. And oftentimes, the performance can be very close to native computation. And hardware-based secure computation essentially can enable very general purpose computation and can enable many different security applications. So with the trusted secure execution environment, we essentially can run the program inside the secure enclave. And then in this case, the operating system and other processes running outside of the secure enclave, they won't be able to tamper with the execution of the program running inside. And also, they won't be able to learn what's running inside, ideally. And hence provides the integrity and confidentiality. And also, the secure enclave can, in this case, provide a hardware-based remote attestation capability where the secure enclave can attest to a remote user what program is running inside the secure enclave and what is initial state. So secure enclave can serve as a really strong cornerstone security primitive for us to build secure systems on top of. It can provide very strong security capabilities, including authenticate itself, the device, authenticate what program is running inside, and providing the integrity and confidentiality of the execution. And it can really be a platform for building new security applications that couldn't be built otherwise for the same practical performance. And there has been many example security applications and systems built on top of Secure Enclave, for example, using Intel SGX, including a lot of great work done here at Microsoft. So besides these example security applications that have been demonstrated, the Secure Enclave can enable. Also here, I want to just briefly mention another usage scenario where Secure Enclave can really help solving even greater problems. So here, many nation-state leaders have recognized the importance of AI and stated that whoever controls and leads in AI will rule the world. So the question is, who is controlling and leading AI today, and who will be ruling the world tomorrow? So here, this is the status quo today. Users' data is being collected, and big companies build personal profiles for users, and then use these personal profiles to serve users. For example, providing driving directions, or even giving a job device and life plans. However, currently, in this setting, these research services, their goal is to maximize company revenue. So the question is there a different future where we can build intelligent agents and virtual assistants that are actually under user control? They can leverage services provided by third parties, and but they maintain the user profile, and they will be serving users driving directions, job advice, and life plans. And the important difference here is that they will be operating under the modes of maximizing user value. So the question is this possible? How can we actually achieve this? So as I mentioned, I wear two hats. So at Oasis, we are building a new technology called the privacy-preserving smart contracts at scale. So what we do here is that we are building a new blockchain platform. And on top of the blockchain platform, one of the key primitive and capability that we provide is what we call privacy-preserving smart contracts. And this privacy-preserving smart contract has a number of unique capabilities and properties. It can provide automatic enforcement of codified privacy requirements. So in this case, the privacy requirements actually will be encoded as code or inside the privacy-preserving smart contract. And also, we can achieve this enforcement without relying on any central party. And so we plan to build this privacy-preserving smart contracts to be able to scale to real-world applications, including machine learning, even at cloud scale. And this primitive of privacy-preserving smart contracts can make it much easier for developers to build privacy-preserving applications without having to be a privacy expert. And in order to enable this privacy-preserving smart contracts at scale, the Oasis blockchain platform provides a number of different uses a number of different technologies to provide this capability, including in confidentiality-preserving smart contract execution, which essentially protects the execution of the smart contract from leaking sensitive information during the computation process. And also, at the application layer, it provides privacy-preserving data analytics and machine learning, including providing differential privacy for the application to prevent the output of the computation from leaking sensitive information about the inputs. And we also develop new architecture and technology for the blockchain platform to enable scalability, to enable scalable smart contract execution. And with this privacy-preserving smart contract technology, we can build a blockchain of intelligent smart contracts where we can actually have various machine learning smart contracts that actually run on top of the blockchain, the Oasis blockchain platform. And these machine learning smart contracts essentially can help pull data from potentially mutually distrusted data sources to together then build, for example, differentially private financial service models, fraud detection models, or even medical diagnosis and treatment models. So one of the key capabilities of enabling this privacy-preserving smart contracts is the ability to do confidentiality-preserving smart contract execution. And one of the key ingredients to enable this confidentiality-preserving smart contract execution is to leverage the capability of secure hardware. All the hardware manufacturers have recognized the importance of building secure hardware. So over the years, they have all been developing different solutions for secure hardware, including Intel SGX. However, today, we still have lots of open challenges in building secure hardware. So first, how secure can it be? Under what threat model? And what would you entrust with the secure hardware? For example, your Bitcoin keys, your financial data, or your health data. And in fact, this is, I would call a grand challenge, is can we actually build a truly trustworthy secure enclave that can serve as a cornerstone security primitive, that can be widely deployed and enable secure systems to be built on top. If we can achieve this, it can truly usher the entire community into a new secure computation era. So what's the path to trustworthy secure enclave? There are several important steps. So first, we need an open source design for the secure enclave. And ideally, we would like to have formal verification for the security and correctness of the secure enclave. And also, we need to ensure secure supply chain management to ensure the security of the manufacturing process. It's very important to have an open source secure enclave design. Currently, none of the commercial secure enclave RT solutions are open to the public. And hence, as the public, we actually cannot analyze or verify a hardware vendor's design in this setting. And also, currently, there's no industry agreement on what is the right solution for building a secure enclave. With the open source secure enclave design, it provides the transparency that's needed for the whole community to together analyze and verify the security and the correctness of the secure enclave and to enable high assurance. And open source helps build a whole community. So there has been great efforts on building secure, open source secure hardware. One example is Sanctum from Srini's group from MIT, which builds a secure processor design using RISC-V ISA, and it's designed to be able to defend against the cache-based side channel attacks. So extending Sanctum, we now have a new project called the Keystone in collaboration between Berkeley and MIT, and there are other institutions who will be joining the team as well. So the Keystone Enclave is an open source, we are building an open source secure enclave on top of RISC-V, and in particular, leveraging the existing physical hardware capabilities already available in today's RISC-V chips. And the goal is to provide strong memory isolation. We want it to be simple and portable, and provides remote attestation capabilities and fully open source. There are a number of goals for the Keystone design, and that are important components to achieve overall the goal of building a truly trustworthy open source secure enclave. And I won't go into the goals, each individual goals in detail, and I think Srini will talk more about the side channel aspect. So Keystone leverages the existing physical hardware capabilities in today's RISC-V chips to build the open source secure enclave. And by using the secure enclave, essentially it helps to enable the system to separate privilege and trust. So in particular, in this case, we actually have three modes: the user mode, the supervisor mode, and the machine mode. And the enclave and also the components that enable the secure enclave are run at the machine mode level, whereas the operating system are running in the supervisor mode, and the other user processes are running at the under the user mode. And one of the key components for Keystone is the security monitor, which actually essentially helps provide the memory isolation. And in particular, we enable the physical memory protection with the machine mode and the virtual memory isolation with the S mode. And the Keystone in particular relies on the standard RISC-V primitives. In particular, there are two main primitives that we rely on. One is the physical memory protection, PMP, and the trap virtual memory, TVM. due to time limits, I probably won't have time to go into the details for these. But so these hardware capabilities make it actually much easier to provide the memory isolation for the secure enclave. And as a result, the Keystone design for secure enclave actually is much simpler than, for example, SGX and also than Sanctum as well. So this is the Keystone architecture. Again, I won't have time to go into the details. Right, so I will actually skip these. And again, because of the fact that Keystone leverages existing hardware capabilities in RISC-V for the memory management, it's actually it can provide much more flexibility in terms of the type of enclave that they can enable, in the sense that the enclave size can be dynamic and where the enclave can be located is dynamic as well. Okay, so due to time limits, I think I have to skip these details, how we actually use the PPM and the TVM to enable the memory isolation. Right. And also, Keystone plans to use the puffs to help with the key management as well. Okay, so right, with the as a collaboration between Berkeley and MIT, so we are working hard on building the Keystone Secure Enclave, and we have a timeline that we hope that in the fall we actually will have a first release of the Secure Enclave, where it won't be full featured. In particular, the first release will contain some of the key capabilities for memory isolation and some capabilities from the secure boot remote attestation and the secure key provisioning. And so we plan to actually deploy it first on the Amazon AWS using FPGA as a first deployment, and later on we plan to have it deployed on the new High-5 Unleashed chip. So using such capability for confidentiality preserving smart contract execution, again, we can enable privacy preserving smart contracts on the Oasis blockchain platform. And using these overall capabilities, we hope to truly enable a blockchain of intelligent smart contracts. And here, let me just give you one example of a sample application that we have been building, and together as collaboration with researchers and doctors from ETH and Stanford for an app called Kara, a privacy-preserving tokenized data market for medical data. So as we all know, medical data is often locked in data silos. So the goal here is that we want to be able to incentivize doctors and patients to share data and to be able to improve medical research. And by leveraging the capability of privacy-preserving smart contracts on top of the Oasis blockchain platform, so in this case, users, patients can upload their medical data in an encrypted form to the Oasis blockchain platform. And then the medical researchers can essentially build privacy-preserving smart contracts. And within the smart contracts, the researchers can include machine learning, model training, and model serving codes. And also, the privacy-preserving smart contracts can specify terms of use. For example, how users may get compensated for contributing their data to the smart contracts, and also stating that, for example, the data will only be used for training machine learning model inside the smart contract. And as users agree with the terms of use, users' medical data can be contributed to the smart contract. As the smart contract collects enough data, it can then run the machine learning model training code to train the machine learning models, and in the end, the medical researchers can then evaluate the trained machine learning models. So in this way, it helps to significantly reduce the friction for medical researchers and pharmaceutical companies to get access to data for training machine learning models to find better cures for diseases. And we have some upcoming paper at conferences. And to summarize, for the technologies that I have been discussing, so Oasis Labs just recently launched. And also, we have launched our private testnet, where we encourage and invite application developers to join our private testnet to build applications on top of the platform. So the carry example that I mentioned is actually a collaboration with some of the dApp developers to build on top of our platform. And with all these technologies at Oasis Labs, we hope to build a privacy-first, high-performance cloud computing platform on blockchain. And all this work for Keystone is in collaboration between MIT and Berkeley. And we have a great team at Oasis Labs. Overall, the goal is that we want to build truly trustworthy, secure hardware that can enable all these great applications. However, as I mentioned in the talk, there are many, many challenges that I actually didn't have time to go into all the details. So more resources are needed for research and development, and it requires a community effort. So let's tackle the big challenges together. Thank you.
Thank you. We have time for a couple of questions. Yes?
Hi, Don. Great talk. How do you plan to tackle the non-technical issues? For example, you talked about verifying the supply chain for building these chips, and somebody may trust a U.S. regulated company like Intel, for example, or whatever, and somebody may prefer a EU regulated company doing that, and somebody a Chinese regulated company. Like, how do we agree on these things that don't have to do much with technology?
Mm-hmm. Yeah, that's a great question. So that's actually another reason why we want to have open source secure enclave. So then in this way, we don't have to rely on any single party. So any hardware manufacturer can then go manufacture it, and different users can also choose which hardware manufacturers that they trust more than others. And also, I do strongly believe that while the whole community will actually already have a lot of experience in many of these other aspects of building secure enclave, but the secure supply chain management is one area where, as a whole community, we actually haven't really tackled it head on. We don't actually have a lot of experience in, but it's a very, very important area. So we hope that with the Keystone project, and also we're actually hoping to build a community together with different institutions and hardware manufacturers as a whole community that actually can be an area of focus in the as a next step in the near future, that we can put in the proper processes and also various verification procedures to help us to make progress towards this goal of secure supply chain management.
Right, let's thank Don again. Thank you. Our next speaker is Professor Srini Devdas from MIT. He's a Webster Professor of Electrical Engineering and Computer Science at MIT. His interests are also broad in computer security, computer architecture, and applied crypto. Srini received the 2017 IEEE W. Wallace McDowell Award and the 2018 IEEE Charles A. DeZoer Technical Achievement Award for his research in secure hardware. He also received the MIT's highest teaching honor, the Everett Moore Baker Memorial Award and the Bose Award for excellence in teaching. So thank you very much, and hand over to you.
Thanks for the kind introduction, Manuel. I want to give you folks a sense of what it's going to take to build secure compute architectures that can do the things that the previous two speakers want to do with lightweight secure enclaves and so on. And it's fairly challenging. There have been many attacks exploiting side channels, but not just side channel attacks, but attacks exploiting out-of-order execution, speculative execution that have come out. And I want to give you a sense of how these attacks work, because we need to understand how these attacks work in order to actually defend against them. So we've been working on defenses against the latest and most potent of these attacks. I'll tell you a little bit about that. And I'll close with talking about secure enclaves. I'll be brief because they've been covered quite nicely by Mark and Don. But the stakes are a little bit higher because in the case of just building conventional processors, you get to trust system software. You get to trust the operating system. And you can make it do work for you that corresponds to handling sensitive data. But you can't do that when you have a secure enclave if you want to minimize the trusted computing base and you want to shrink it down by whatever it is, 2-3 orders of magnitude from tens of millions of lines of code down to thousands of lines of code. So I'll say a little bit about that at the end. So let me just start. You're probably thinking, what is this picture? Well, I had this really pretty picture that described compartmentalization and secure containers in processors, and I realized I probably illegally downloaded it. And so this is a picture of my toolbox. And so I own this picture. And it essentially gives you a sense, more seriously, about what architectures have to do. Architectures have to isolate processes from each other. This is fundamental to multi-processing. It's fundamental to time sharing, right? It's been with us for 50 years. And if this is violated, if architectural isolation is violated, we really have nothing. I mean, we have no security, we have no privacy, we don't have integrity either. And so it's important to maintain architectural isolation. And over the years, computer manufacturers have used many different performance optimizations in order to improve your IPC, instructions per cycle, et cetera. And it turns out these operations were done largely at the microarchitectural level, and they were hidden from the ISA, the instruction set architecture. And in particular, these microarchitectural optimizations have been shown to leak privacy and potentially influence correctness as well. And so let me say a little bit about the latest of these attacks corresponding to Spectre and Meltdown that have obviously received a lot of press. But very briefly here, what one can do if you want to just execute a sequential program is obviously go from instruction I to I+1 to I+2, et cetera. And every once in a while, you're obviously going to have a branch, and that corresponds to control flow. And you could certainly wait until the branch has been resolved, so you know that you want to go in this left direction. But if, in fact, it takes a long time for the branch to be resolved because you have to go look at a memory location, for example, then you might, in fact, decide to speculate. So you decide that you're probably going to go left, and you decide to take that left fork, and you start computing J and J+1 even before you finish up on instruction I. And if you speculate correctly, then everything is great and you've gained performance. But if you misspeculated and you've decided that what you really should be doing is to go right, I should say, you decided to go right, but in fact you had to go left, then you've executed K and potentially K+1, and you have to roll back. And you've done some things that can clearly be cleaned up from a standpoint of architectural state. And there's no question that processors today definitely do this cleanup. But unfortunately, what happens is that while you're executing K and K+1 in this incorrect way, or should I say in a misspeculated way, you may have changed the microarchitectural state, and that could leak information. So this notion of speculation was considered just a performance optimization, but it has serious security implications. And essentially, the attacks that have been proposed, there's just a wide variety of them. I mean, every conference seems to have sessions now, architecture conferences on new types of attacks. But they have two characteristics in common. First, they primarily exploit cache tag state. So you have caches, which are obviously important for performance, and they've been around for a while. Caches are microarchitectural state, and you bring things into the cache when you executed, for example, the k and k+1 incorrectly, and that changes the state of the cache. And the cache state, unfortunately, in speculation, is not rolled back in conventional processors. And because you don't do that, there's some side effects to the misspeculation. The other thing that's interesting is that you have branch predictors in computers that correspond to deciding how to predict which way to go, whether to go left or right. And in this case, you have a situation where the learning associated with the branch predictor, I mean, these are not deep learning engines, or at least not yet, but they definitely have capabilities associated with history tables, et cetera. And the inputs to these branch predictors that correspond to learning which way to go for a particular branch may come from other processes. So it's not just there's no isolation within the branch predictors on learning from your own process. And that is actually also being exploited in these attacks. So there's really a huge attack surface. And so this is really a picture that I won't spend so much time on, but I'll leave you with spies potentially everywhere because you have processes that are sharing branch tables, processes that are sharing caches, DRAM controllers, there's timing channels, cache tags, and so on and so forth. So this is a fairly exciting time in computer architecture, primarily because we have to go back and rethink how we would do time sharing in the context of all of these spies. I want to give you a sense of how to categorize these different attacks. And so here's a little picture that taxonomizes attacks corresponding to both the new ones and the old ones. And so the idea here is that you have a domain, you have protection domains. That's really what time sharing is about. So you have a domain of a victim. The victim has some secret that the victim wants to touch and use for encryption, or maybe it's just sensitive data, medical records, what have you. And then you have an attacker. The attacker is concomitantly using resources of the machine. It may simply be a time-shared situation. You may only have a single core, but they also could be multi-cores, and they could be space sharing as well. So these two domains are supposed to be separate. You have two different domains corresponding to the victim and the attacker. And the first thing is that there's these channels. And these channels are these side channels that have to be created, and then any number of them, cache tag state, the most common at least in current day attacks. But there are others as well. And what the attacker does is it creates a receiver. So this is really a piece of code that can somehow exfiltrate through this channel the secret or some form of the secret that is in the victim's protection domain. And there's also a transmitter that's associated with a piece of code, and I'll tell you a little bit more about this in a second, that touches the secret. So this transmitter is actually running in the victim's code. And so it has permissions associated with that. Right? And so the basic idea is that if you create this transmitter and this receiver and you have this channel, well, you've essentially broken privacy of the victim. And so if you look at the different attacks that are out there, and so just to give you a sense of why this taxonomy is broad and incorporates both the recent attacks and attacks that are 20 years old, let me give you a sense of an age-old attack that was done about 20 years ago on the RSA encryption algorithm, where it has conditional execution. Depending on what the bit of a key is, you either do a modulus or not, roughly speaking, and you do a lot of computation in one case going left, and you don't do very much going right. And that this is a problem because this is part of the algorithm, and this algorithm is actually doing different things based on the secret key. I mean, it has to, because obviously the output has to depend on the secret key. But if you haven't written the program in such a way, you could be in a situation where regardless of speculative execution, you're just doing more work on the left-hand side versus the right-hand side, and the microarchitectural channel associated with the cache could change the execution corresponding to what the execution would be if the secret key bit were 0 versus 1. So this change with respect to going left or right is exfiltrated through the cache tag channel based on cache hits and cache misses that can be viewed by the attacker. So you can get a sense of what the victim's cache hits and cache misses are based on what your cache hits and cache misses are if you share the cache. And so this was an attack that was done 20 years ago, and the fix for this attack is something that Mark mentioned. You can try to do oblivious execution by balancing paths, et cetera. And you can certainly do this for RSA. But as you'll see, cryptographic algorithms got a lot more complicated, and these attacks are still valid in the case of anonymous attestation schemes like SGX, and I'll get to that a little bit later. Now, you can take these attacks corresponding to Spectre and Meltdown, and you can view this in this taxonomy by thinking about Meltdown as being something where the attacker was able to write this transmitter by essentially creating a permissions check before accessing some data. And because of speculative execution, that data was actually accessed and brought into the cache in a particular corner case before the permissions check was actually validated. And so that was a corner case in the processor pipeline that corresponded to the Meltdown bug. And Spectre is a broader class of attack where you can actually synthesize this transmitter by looking at victim code. It's broader. It's also harder to accomplish. But it's something that clearly has been done, at least in let's say, at the test tube level, if not in the wild. And so these things are things that, just from a purist standpoint, are things that you need to fix if you want architectural isolation the way it was promised to us 50, 60 years ago. So how do you defend against these types of attacks? I'll just focus on the cache channel because that's the most popular channel for exfiltration. And it's a matter of carefully designing processor caches, in this case, to do perfect isolation. Right? And so people have done cache partitioning, and there's cache partitioning schemes that are in processors. And in general, to protect against these attacks, the defense schema would be that you have to block one of these steps. I mean, you got to break that pipe there. And we've focused on, in our research, focused on blocking the channel. That seems like the easiest thing to do, but there's other ways of defending as well. And so Intel has cache allocation technology built in. It's abbreviated CAT. And essentially, it's something that is a quality of service mechanism. It wasn't meant for security, but it's a way of making sure that a runaway process doesn't trash the cache for you, and you still get performance even though you're using only part of the cache. You at least get one part of the cache. Now, Computer Architecture 101, caches are made up of sets and ways. You can think of the sets as being horizontal rows, but what you see here are different colors corresponding to the ways. And essentially, a way is something that says if you have two ways, then you can either go here or there in a particular set, and it's associativity. And so you can partition the cache using sets or using ways. CAT does it using ways, and it says that you can essentially say that the attacker cannot evict a piece of data from the victim's way. That's essentially what CAT does. It's a quality of service mechanism. Not quite enough for isolation, for perfect isolation, for a couple of different reasons. The first is that shared addresses are visible. So it's possible that you have some shared libraries, and the victim and the attacker could be sharing data, and that corresponds to data that's in the victim's way, for example, because the victim accesses it first. And so it's possible that that won't get evicted, but you can see the cache hits associated with these shared addresses. And then the other part is just a little bit more subtle, is that you have replacement policies associated with these caches. LRU is the policy that you learn about in Computer Architecture 101, least recently used, but nobody builds LRU, at least not perfect LRU. They approximate it. And it turns out that replacement metadata can leak information even though you had isolation in the ways or you had isolation in the sets. So I'm not going to go into gory details here, but roughly speaking, the first reason that CAT leaks information and it doesn't protect you is simply that cache hits are not isolated across domains. So in the shared address case, if an attacker brought a piece of shared data into its way, the victim will hit on it. And if the attacker didn't, then the victim would miss on it. And so you get some information from that. And then because you use approximate LRU schemes, even though you have this partitioning of blue and red over here, the first three columns here, or the slots, correspond to one domain. The red one corresponds to a different domain. And you can think that there's isolation, but if you have an approximate LRU scheme, a PLRU, pseudo-LRU, which is used quite commonly in various processors, it's possible that you can sense a difference in what was evicted from the victim, even though you had this isolation because of the replacement policy at having imperfect isolation. So, so cat doesn't protect you, and so we had to improve it, and so we said, well, we'll call it dog, right? So we want to be it's just an abbreviation, dynamically allocated waveguards. It's a way of taking the cat mechanism and fixing these two things that I've told you about. And just briefly, I just have one slide on it. You have to track global protection domains. You have to be very careful about what goes into the cache and what gets evicted from the cache. And you can do this by essentially making sure that cache tags or replacement metadata don't interfere with each other. It's a fairly simple change. Hardware manufacturers would tell you that this is an invasive change to the hardware because you're messing with the cache hash function, et cetera. But I am a proponent of open source and clean slate design, so for us it's easy. But it's not something that can be done. Any change in hardware obviously takes years to deploy, but this is not something that would be as invasive, I would say, as changing the processor pipeline and changing the number of stages, for example. And so roughly speaking, you have additional data associated with what gets evicted and what gets pulled into the cache, and also the replacement policy. Perfect LRU does not have a problem. Random replacement doesn't have a problem. But if you use an approximate LRU scheme, you have to do a little bit more work to ensure perfect isolation. And so now you'd say, OK, this was the cache tag channel, and I'll just leave you with all this other microarchitectural state, including branch predictor state, that needs to be isolated if there were attacks that were potent enough to exfiltrate through those channels, and you could use this type of technique over there. Again, you have to look very carefully at what you bring into how you modify the microarchitectural state. There's a little bit of a complication. The unfortunate part of the dog scheme that we derived is that you're disallowing hits across protection domains. So if you have some shared addresses, then it's possible that these shared addresses would be replicated across ways, so the same address in two different ways of the cache. And this is OK for read-only data, but obviously it would be a problem if you guessed wrong and the data was writable. And so you have to do some work with the operating system to try and fix that. So let me close by just briefly telling you about what the challenges are in building secure enclaves in speculative processors. There's been this material covered in a couple of different ways. So very briefly, we want to shrink the trusted computing base. You don't want all of the operating system to be trusted. You'd like to minimize that to perhaps a security monitor, as is the case in Sanctum, or the microcode, as is the case in Intel SGX. SGX has some nice properties associated with it. It does all of these things and shrinks the trusted computing base, but it has some serious issues associated with side channels. It leaks privacy in many different ways. Microsoft had a very nice paper that was mentioned on the leak through the page tables, through the page fault mechanism, but there's other ways, and hyperthreading, for example, is yet another way, and we've already talked about speculation. Unfortunately, all of these things have gotten to the point where now you can take SGX machines, or at least rumor has it, since I haven't read the paper, but it's going to come out August 14th, and you can extract private keys from SGX machines when the machine is running anonymous attestation using EPID, because those paths that I talked about back in the RSA example weren't completely balanced, and therefore there's these microarchitectural channels, exfiltration through the cache, and also through out-of-order execution. So a subset of the people who did the Spectre attack have published this paper that's going to come out, as I mentioned, on August 14th at Usenix Security, which are essentially breaking the SGX ecosystem. And I think the title of the paper is something like extracting the keys of the Intel SGX kingdom or something like that. So, so that's not very satisfying, obviously. So there's work to be done. This wasn't because we were smart. It was probably more because we were lucky that we decided that we would build speculative, non-speculative processors way back when we started our Sanctum project. Speculation is hard to build in hardware. We knew about a whole bunch of other attacks, and I don't know of a way of isolating hyperthreaded applications from each other, so we decided we wouldn't do hyperthreading either. But we did definitely look into the cache tag channels, and we have partitioned caches in Sanctum, and we clean up after ourselves in terms of the time-shared processes. I want to say a little bit about the Sanctum's chain of trust. Don mentioned this. So the idea really here is that you build processors that have, again, public keys and private keys associated with them. The way it works in Sanctum is that no one knows the private key. It's generated randomly when the chip is fabricated, or the chip is powered up, I should say, or on an FPGA. And privilege doesn't imply trust, but you do have machine mode where this small piece of code called the security monitor runs, and it essentially verifies all of the allocation decisions that the operating system makes. And you can get secure enclaves using this mechanism. And of course, the key question is, what's your threat model? Did you incorporate all of the attacks that are possible today in the threat model, and did you design for that? And it's simply armor and ammunition. It's going to keep going. I don't see an end to that. Again, Don mentioned this. The page fault attack is an important attack. It's, I would say, a design flaw in SGX. We fix it a couple of different ways in Sanctum versus Keystone. In Sanctum, there's two sets of page tables. The enclave page tables are inside of enclave memory, so that sort of fixes this page fault attack in the sense that you can't see those addresses. But there's other ways of doing it, including, as Don mentioned, using the physical memory protection primitive in RISC-V. And so just to give you a sense of what it takes to build an enclave, I've shown you this picture, obviously not parsable here, but the colors are what you want to look at. Those are the things that changed, really, the interfaces. We needed reset logic for all of the orange colors, and then we needed to add a little bit of logic corresponding to the blues, right? So it's about a 2% change. This is what I meant by it's not invasive, at least from my standpoint, in terms of actually taking a processor, a stock processor, and putting enclaves on it. And so let me just tell you about status and close. Sanctum is released. It has limited functionality, but it provides secure enclaves. You could run it on Amazon Web Services, F1 instances that have FPGAs. We invite you to, we haven't done an official release yet, but that's happening. Don mentioned Keystone, which is, I guess, next generation. I would definitely like to look at building a speculative out-of-order processor. It's not going to be very high performance because it's academic work, but it's interesting from a standpoint of what does it take to go build something that's resistant to Spectre meltdown attacks without the cop-out of saying, well, we don't do speculation, so we protect against them. Adam Chipala gave a nice talk yesterday about his system, his COC system, and he's doing open source cryptographic primitive verification. We have open source hardware. It'd be wonderful if we could marry those two. And Adam and I and Arvind at MIT have a DARPA project on doing that. So that's all I had. Thanks for your attention.
Thank you.
Yeah, Christos.
At the hardware level, we eventually design mechanisms, right? And then somebody has to build policy and so on. And traditionally, we've been lousy at making sure that software people use things correctly. Maybe we're missing the right way of documenting things, tools automatically change. The most canonical example is that we thought that OS and user data should never get mixed with each other. Then some OS person thought there's a cute caching optimization or something and mapped the kernel data into the user address space, and there is Meltdown and Spectre. Okay. Any ideas about how to automatically check for unsafe user to encourage people to use these mechanisms the right way?
Yeah, so I think if you look at these native client type approaches, right? I mean, that's the best answer I have. Where I think you want a runtime inside of the secure enclave, and I think Don may have mentioned this as well in passing. Inside of the secure enclave, actually no, it was Mark who had this picture. Inside of the secure enclave, that's actually sanitizing, what this enclave does. And so no, I'm a hardware person. I do not want to write that piece of software. But I think that you want to have essentially an environment that unintentional errors. Obviously, there's badly written programs, but you also programs sometimes do silly things, and if you want to protect people from their silliness, you have to have some sort of layer on top of it. So I think that's kind of the right way of doing it, right? Okay, good. Don just said they'd do it in Oasis. Okay. All right.
Right, we have time for one more question while I plug in the power to my laptop. No more questions? One question, yes.
How much slower does a machine without speculation and hyperthreading run than a normal processor?
Oh, I'm sorry. I stopped paying attention. Sorry, can you repeat the question?
How much slower is the processor without speculation and hyperthreading?
Oh, it's not that much. I mean, I think we're talking, hyperthreading would be about 20%. Just hyperthreading would be 20%. And it's a little bit unclear as to where that 20% comes from, the improvement. Speculation, out-of-order speculation is more than that. I mean, I would hazard that within a factor 2.
Okay.
Much higher. Right. Much higher. It's much higher than.
You can get much better than 2?
Having no speculation, its impact would be much higher than 2x.
He knows more about abstraction than I do.
Thanks.
But I think the way that we've thought about doing this is really, I mean, there's also simple cores. There's this other philosophy that says you can have simple cores and you have a lot of cores. And you make the software a person parallelize his or her application. Right? Yeah.
All right, thank you very much.
All right.
Let's thank Srini again. So our next speaker is Peter Pichuk. He's a professor at Imperial College London. Peter leads the large-scale data and systems group in the Department of Computing. He has done a lot of research on scalable, reliable, secure, large-scale software systems, including publications at an impressive range of conferences, including OSDI, VLDB, NSTI, and many others. So we're very fortunate to have him here and talk about SGX. Thank you.
All right. Thank you very much for the introduction, Manel. Okay, so what I would like to talk about today is some work that we've been doing over the last couple of years on thinking how to provide system support for trusted execution in a cloud environment. And so what got us excited about the trusted execution model, that it essentially deals with the problem that a tenant can move to a cloud environment without having to implicitly trust that cloud provider. But the question here becomes, what system support needs to exist in that cloud environment so that you can actually move existing workloads? And so the issue is that a cloud tenant would effectively think of the cloud environment as an untrusted black box. So there's a very large and complex stack that the cloud provider runs with millions of lines of code. And obviously, this is where a large number of security issues can come from. So when you have vulnerabilities in the hypervisor, in the OS kernel, and so on, they can be exploited with a large range of attacks. And then similarly, there's the issue of insider attacks, where people who have privileged access to the cloud environment themselves can then compromise the tenant applications. And actually, when you think about existing hardware security mechanisms that we have, they don't really try to address this problem directly, because the regular model is that the cloud provider actually doesn't trust the cloud tenant. So a lot of the isolation mechanisms that we have, they're all about protecting the privileged part of the cloud infrastructure from tenant applications. But this is essentially what the cloud tenant wants is the reverse. So this is what we thought is exciting about trusted execution, that it's a dedicated security feature that actually gives control to cloud tenants to protect their applications and their data. So one way to see this when you look at SGX as an implementation of trusted execution, it's actually a user space concept, right? So you don't need to be a privileged process if you want to create an enclave, and that enclave memory is then encrypted and integrity protected, and only the protected code can access that memory, but the hardware will prevent access from higher privileged parts of the environment, such as the OS kernel or the hypervisor. Right? So cloud tenant can directly, ideally, take advantage of this hardware feature. But the question becomes, so if you are a cloud tenant, you want to move a particular workload to a cloud with trusted execution, you want to take advantage of this model, how can you do this without modifications to your application? Right? So the question here is, what is the support that should exist in that cloud environment so that people can actually use trusted execution or Intel SGX? So what we've been doing is exploring this design space of different types of system support that we could offer to cloud tenants. And there are kind of a couple of things that one can do. So probably one of the earliest approaches that was proposed, I would call the library OS approach. So this is represented by work that Microsoft did on a system called Haven, where you effectively take an application with all of its dependencies and an entire library operating system, and you place this inside of an SGX enclave. So then you have effectively a self-contained way of supporting that application inside of the enclave, and then you're only exposing a very thin hypercore-like interface to the outside to do, well, some low-level I/O operations where you rely on the outside environment. So when you think about this model, it has a very clearly defined interface to the outside, but you potentially have a large trusted computing base because of the library operating system and all of the system support that you're putting inside of the enclave. So we've been exploring that model with a system called SGX LKL that I'm going to talk about more in a moment, that is a library OS for supporting unmodified Linux binaries that execute in SGX enclaves. So another way of designing system support is to take a slightly different approach where you reduce the trusted computing base by only placing the application, its library dependencies, and a standard C library inside of an SGX enclave. And so this is something that we've explored in a system called Scone that does this for supporting Linux applications inside of SGX enclaves. So now the interface that you're exposing to the outside world is essentially the system call interface. So it's a much broader interface. There are more calls that are exposed, but you've reduced the trusted computing base because inside of your enclave, you only have a standard C library, but you no longer have the library operating system. And then finally, you can think of partitioning your application as sort of the furthest that you can go in terms of reducing the trusted computing base. So here what we're doing is we're taking an application, we're only taking the security sensitive functions of that application, and this is what we're placing inside of the SGX enclave. And then we have an application specific interface to the outside world of function calls so that the security sensitive functions can interact with the rest of the application that runs outside. So this gives us a small trusted computing base, but it does also incur a more complex interface to the outside world. And so the SDK that Intel released for creating SGX applications follows that model. It essentially gives you an RPC-like mechanism for placing some functions inside of an enclave. So a piece of work that we've done is a framework called Glamdring that I'll also talk a little bit about, that tries to help developers making the decision which functions from the application to place inside of an SGX enclave and what to execute outside. Okay, so let's talk a little bit more about the library OS approach. So what are some of the challenges with that? So one significant challenge is performance, because enclave transitions by themselves, they're expensive because the hardware has to perform particular checks whenever execution transitions in and out of an enclave. And since we have to exit an enclave whenever we want to invoke a system call, we will naturally incur those expensive transitions when we run a particular workload. And so this performance overhead can be quite significant. So this is an experiment that we did where we measured the rate at which we can execute system calls when we increase the number of threads, comparing native execution with SGX. And you can see that you're losing about an order of magnitude in terms of performance when you have SGX enclaves. So for a system call heavy workload, this is a significant problem. So what can we do about this? Well, so one obvious idea is simply to reduce this number of enclave transitions. So try to avoid exiting an enclave and instead have threads stay inside of the enclave. So the more we can stay inside, the less we suffer from that performance cost. So how can we do this? Well, so one thing that we've done, we use user-level threading inside of SGX enclaves. So instead of relying on hardware threads and preemption, we have user-level threading, and those threads essentially never exit the enclave, and instead we have a scheduler inside of the enclave that switches between those threads. And that results in a significant performance benefit. And the other thing is to move some OS functionality inside of the enclave, right? So thread synchronization is one example, memory management, file system, signal handling, and so on. So things that normally would invoke a system call or interaction with the outside operating system. If you can move this inside of the enclave, you avoid those expensive exits. So this is so these are the ideas that we've then realized as part of SGX LKL that provides system support for enclaves. So SGX LKL can run unmodified Linux applications. So you take an application, all of its dependencies, you provide this as an encrypted file system image, and you can then launch it inside of an enclave. And so the way SGX LKL provides a library operating system, that it actually uses the Linux kernel as a library. So it uses, it's based on something called LKL, the Linux kernel library, which is an architecture-specific port of the Linux kernel, and we can run this entirely in user space inside of an enclave. So by doing this, we, for example, get a trustworthy file system and a network stack that we can then exploit for SGX. So there are a couple of interesting features in the SGX LKL design. So one is that user-level threading. So we can do thread synchronization within enclaves without exiting. So we have a Futex implementation inside of an enclave that we can use for this. So the other thing that we do, we support asynchronous system calls. So whenever the application actually needs to execute a system call, because we have user-level threading, we can ensure that the system call request is simply put into a queue that is shared with the outside, and we can schedule a different thread while we're waiting for the result of that system call. And that can also improve performance. And this is a technique that we've also explored in the work on Scone. And then finally, we have a custom memory allocator where we essentially do our own memory management, both for the kernel and the enclave application inside. So I have one picture on the SGX LKL architecture. So this is what an enclave looks like when we're running an application. So we have that encrypted file system image with the application that we want to run. And then we have the LKL library inside of the enclave, and in addition, also a standard C library. So when we are launching an application using SGX LKL in an enclave, we will first create that enclave. We will then load LKL. We will boot the LKL kernel inside of the enclave, and then the kernel will mount the encrypted disk image with the application, and it will invoke a dynamic linker loader to then load the binary into the enclave. So when the application then executes, it then can invoke functions of the standard C library, and then whenever those functions need to run a system call, then this will then become a function call in LKL, and it will execute the functionality within LKL. If then LKL needs to interact with the actual hardware, because, for example, it needs to do an I/O operation to read a disk block, or it needs to send or receive a network packet, this is then done through a set of shared queues that we have with the outside world using our asynchronous system call mechanism. And so this gives us a significant performance improvement compared to a model where we would exit the enclave. There are a couple of other things that we had to worry about. So another one is signal handling. So we need to have signal support, but the problem here is that whenever the process receives a signal, it's actually delivered to the outside. So what we do is register a permissive signal handler on the outside and then demultiplex the signals inside so that we can deliver them to the correct user-level threads inside of the SGX enclave. So with this model, we can now provide a trusted Linux file system inside of the SGX enclave. We can actually support any file system that is that is included in the Linux kernel. And for the encryption and integrity protection of the file system, we can use standard Linux facilities, like, for example, the device mapper API for encryption and integrity protection. So similarly, for the network stack, we can do the same thing. So we can support any network protocol that is supported by the Linux kernel, and then the actual encryption of packets can happen at a lower layer in the network stack, so we can use layer 2 or layer 3 encryption of the raw packets. So when you look at the interface that we're exposing to the outside world, it's quite a thin interface. So we can subdivide the calls into workload-independent host calls. So they're calls that effectively will be called during the boot up of LKL, but they're independent of the application workload that we're running. And then we have some workload-dependent calls, so mostly related to block I/O and network I/O. So the reason why this distinction is sensible is that obviously that host interface itself is a side channel. So we need to worry about protecting those workload-dependent host calls and ensuring that they don't leak any information about what is happening inside of the enclave. And this is, for example, one piece of ongoing work that we're doing is that we're asking the question, can we make this host interface itself oblivious? So can we make sure that an attacker that will observe the entire sequence of host calls will not learn anything about what is happening inside of the SGX enclave? So SGX LKL is available as open source on GitHub. So you can play around with it. You can launch Linux binaries from an Alpine Linux image. And the other interesting thing is that we have support for managed language runtime. So you can use SGX LKL to run the Java virtual machine or the VA JavaScript engine. So you can effectively run Java applications inside of SGX enclaves. Okay, so this is an example of using a library operating system to support cloud applications. Now let's look at the other extreme of partitioning an application. So why is that an interesting thing to do? Well, so what about if you want to run a really large cloud application inside of an SGX enclave, right? So let's say we want to support, Apache Spark inside of an SGX enclave. So here we're looking at a large amount of code. If we place all of this inside of an enclave, for example, using SGX LKL, we're potentially looking at many vulnerabilities that would be in that code base. So instead, what we would like to do is simply identify the security-sensitive parts, which is the data that we're processing and the job implementation, the task implementation of the analytics job that we are running. And so in the research community, there are many examples where people have partitioned applications for SGX manually. So we've done some work on a system called SecureKeeper that partitions Zookeeper into a security-sensitive part and an untrusted part. Microsoft did some work on partitioning MapReduce. So there are many examples where people do this by hand. But what we were interested in is, can we help developers to ideally automatically determine the minimum functionality that needs to be run inside of an SGX enclave to enforce a particular security policy. So we've created a SGX partitioning framework called Glamdrink, and it's a compiler-based framework for partitioning C applications at the source code level. And it works by executing a number of steps. So it relies on a developer first annotating what the security-sensitive parts are that should be protected. So this is essentially the security policy that a developer needs to express. So once they've done this, there's static analysis that we perform at the source code level to then understand which parts of that application that need to be protected. And then we rely on source-to-source transformation to create the enclave part of the application and the untrusted part. So let's briefly look at this in a bit more detail. So first you need to provide the annotation, and this is simply a source level annotation. So in the example of Spark, let's say you want to protect the data that initially is encrypted and sits on HDFS. So, so you would provide an annotation in the Spark code before it's being read by the framework. So you can add a pragma that says that data is sensitive and should be protected throughout the execution of the application. So the way we then use those annotations is that we use them as part of the static analysis to figure out how to partition the application. So we generate the program dependence graph that captures all of the data and control flow dependencies between different parts of the program, and we start our analysis at the particular nodes that were annotated by the developer. And to ensure data confidentiality, we're interested in everything that is affected by sensitive data. So we do a forward data flow analysis. To enforce a integrity policy, we essentially do the reverse. So we do a backward data flow analysis to understand everything that may impact a particular result that we want to protect. And so then what we need to place inside of the enclave is essentially the union of that analysis. And this is then what we consider to be part of our trusted computing base. So we then automatically rewrite the source code to implement that partitioning, and we do this using the LLVM compiler toolchain by then rewriting the application and essentially adding the appropriate enclave and outside calls so that we can do the transitions when we move control in and out of an enclave. There's actually one last step that we need to deal with, and this has something to do with the fact that we rely on static analysis for this partitioning. So static analysis obviously makes assumptions about, for example, valid execution in the semantics of the programming language. The problem is that an attacker has complete control over code that lives outside. In particular, they could violate those invariants the static analysis used. And so therefore, we need to make sure that whenever control moves into the enclave, those invariants actually hold. And the way we achieve this is by adding runtime checks that simply verify that the partitioning is still sound based on the assumptions that the static analysis made. So one slide on some results. So how well does this work? Well, so we did an evaluation with 3 applications, Memcached, Digital Bitbox, which is a Bitcoin wallet, and LibreSSL, a TLS implementation. And we applied Glamdring to partition the application. And the outcome was that between 22 to 40% of the application is then placed inside of the enclave, and the rest is outside. So obviously, there's no magic here. It depends ultimately on how your application is structured, how powerful your static analysis is, and this will then determine how big the trusted computing base will be. But it's definitely a way of helping a developer to effectively obtain a principled way to decide which functionality they want to protect using an SGX enclave. So to summarize, so trusted execution in our eyes has a lot of promise in terms of dealing with real-world cloud security problems today. But at the same time, it also creates new challenges in terms of system support and also tool support to take and port applications that we have and secure them using trusted execution. And so if tenants want to run unmodified existing applications, so approaches that, for example, use a library operating system can help with doing this and effectively doing it transparently. But at the same time, it is also important to think about how to integrate appropriate tools with development environments for new types of applications. And the work that we've done on Glamdring with static analysis is one example of achieving this. Okay, so this is all I wanted to share, and I'm very happy to take any questions. Thank you.
Thank you, Peter. Have time for a couple of questions. Yes?
How do you ensure that control eventually comes back from trusted enclave back to the untrusted code? Because it's possible that you might know an add-on back where you get stuck inside the trusted enclave and the external OS cannot even look into it.
Yeah. I mean, so the thing to keep in mind with trusted execution models like SGX is that they don't really have they don't focus on availability, right? I mean, so they don't give you any guarantees in terms of availability. So an outside attacker that, for example, controls the scheduler or the operating system can simply withdraw resources from the enclave. The enclave relies on the outside scheduler to run, right? So effectively, the enclave cannot launch a denial of service attack because its scheduling relies on the outside operating system. But in general, in all of those approaches, they can't defend against denial of service attacks.
One more question. Yep.
Could you say something about the memory footprint of LKL, particularly with all Linux kernel and then doing all your block IO maintenance?
Yeah. Well, I mean, it's actually not as bad as one would think, because obviously one advantage of Linux is that it has been optimized for embedded architectures, and essentially it can run in low memory footprint. So if we run SGX LKL, we can fit it within current EPC sizes actually quite comfortably. So it fits. So it uses less than 96 megabytes. For some of the larger applications, we will run out of EPC memory, so we will use SGX paging, and there the performance very much depends on whether your working set will fit within the EPC or not. And again, for some workloads, that's the case. Obviously, once you run complex Java applications with the JVM, I mean, at some point with the current SGX implementations and the memory limits, you will see lower performance. But there's no fundamental reason why future SGX implementations could not have larger EPC sizes.
Right. Thank you very much. Let's thank all the speakers, and this concludes the session. Thank you.